What would be an example of something where they set C equal to 1 or H bar equal to 1 or what have you, and it turns out it's incorrect under what you've investigated?
It's not incorrect. You see, this is misleadingly. If you do the calculation correctly and do everything correctly, it's not the problem. You just lose the physical meaning. So, for example, do you know the Dirac equation?
Yes.
What does it tell you? What is it saying? So if in that, instead of the gamma, right, the gamma is these matrices that sort of sum to 1. Put a C in front. Now, that C gamma is actually a velocity that comes from the boost of the spin part. So the gamma is telling you what is velocity of the spin going. And then you have a partial derivative, put the h bar, that's momentum. So it's velocity contracted with the momentum of the particle equal mc squared. Right, so it's basically telling you, all these things is telling you that v times p equal is going to give you mc squared, because you have the momentum, which is mv, and then you have the velocity is mv, but you're contracting together those vectors. The norm of v square is going to be c. So you're just saying, something that you already have in classical particle mechanics in a relativistic setting, that the inner product between the momentum and velocity is equal to mc squared. That's it. It's just that you're saying in the context of field theory, so of course you're going to use a language that is a lot more complicated, but the physics that you're describing, what the equation is telling you, is just that. There is nothing more. And so what I feel that we have done by essentially stripping all these things away and just following blindly the mathematics and looking for mathematical structure for new theory, I think we're just losing all the physics. They're still there. And if we did it in the way that we used to do physics, right? Because these assumptions are just a new version, maybe like more rigorous version of Newton's laws and the laws of thermodynamics. Like we used to do physics like that. You figure out you boil the world into these assumptions that you're making, or these starting points, and then get everything from there. And you keep track of what it is that you're doing. You check your, when you're doing undergrad problems in physics, you do the dimensional checking where, to make sure that your masses are masses and that suddenly didn't become velocity and so on. So why are we not doing it in the more complicated theories where we can even get, more confused because it's all abstract math and so on?
Well, I understand that you want to make sure at the end that the units match up on both sides of the equation. But I don't see what would be an example of something in mathematical physics. Say, the standard model, we set C equals to 1 and H bar equal to 1 and so on. Yeah. And it's the most predictive of all the models that we have.
You're just choosing a specific type of units in which you're doing the calculation because they're more convenient. So that's what you're doing.
Okay, what I mean is, I don't know if you saw the Iceberg and string theory that I did.
I understood more about string theory by looking at that than talking to actual string theorists.
Okay, well,
can you give me an overview that it was better than what other people give? So,
okay,
please go ahead.
Thank you. At any rate, at some point you get n equals 4, super Yang-Mills theory in 4 dimensions and so on, and there are different results. So what I'm saying is, in those results, is there something that they're doing that is incorrect? Now, outside of the complaint that there is no supersymmetry that we find, and this is assuming strings at a base, even though what I just said was not assuming strings, the Yang-Mills case. But you get the idea. So what's something that is quite advanced in mathematical sophistication that is incorrect? I understand that for us to gain insight into what this is saying, what this means, reintroducing units is useful.
Correct.
But is there something wrong at the mathematical level? Like, is there something that we've gotten incorrect?
I get you. So there becomes a little tricky because that's not my job. So to be able to make the claim, I would have to know string theory enough to be able to say that, or any other physical theory. And I don't have the level of knowledge that, that I need that. But I can tell you this. Remember when I was talking about the real numbers? The assumptions that we have to put there are very idealized, right? And there is no way that all those assumptions are going to hold if we are looking at something at Planck scale. And if you remember before, I said that the hard part was getting the ordering right, was not getting the real numbers, it's getting the ordering.
Right.
And so what needs to happen is that when you go at Planck scale, you are going to lose completely the notion of ordering, which also means you're not going to be able to define real numbers for things that you go and measure, because you're not going to have ordered quantities. So I don't know what structure we're going to have, because I don't have enough constraints to know what needs to happen. I don't know what are the things that I can assume to be valid at that scale. But I know that at that scale, the assumptions that you need for the real numbers are going to implode. And therefore, if I have a theory that says, oh, yes, this is going to work at Planck scales, and I see that they're still using real numbers for quantities, they're using integration, right? Because how can you have a differentiable structure if you don't have the structure of the real numbers underneath, right? So there are all these pieces that assume underneath the real numbers, and I'm pretty sure all those pieces are going to go. So if you have a theory, whatever it is, that claims, oh, this is going to work at Planck scale, and it's still using differential geometry, real numbers, and so on, from what I know, I would be extremely skeptical. But I can't tell you any specific theory, because I would have to go and look at the data. So I can't.
Now, what about Dirac's equation? Does it not assume the real numbers? It's a differential equation.
Yeah, of course, yeah.
And that is also about the quantums. So how does that work? If it's easier to go to Klein-Gordon, feel free to go to Klein-Gordon. Doesn't any of them?
It doesn't matter. So the issue there is that you are doing, even in quantum mechanics, you're still using real numbers. Right? So you're still making this assumption that you have references and you can put them up, and you have a scale that it's perfect, and you know what number is greater and below. And so, yes, these structure, I would think that they have to fail as well.
They fail at what point? Like, what does it mean that they have to fail? Experimentally.
That they do not... So here's how I think of physical theories, which is at this point very different from what people think about the different things. For me is, I have a system in front of me, and I assume that some things are valid for this system. So for example, let's say in electromagnetism, we have the charge distribution, right? And you think that as a field, that is a charge density, okay? Well, that's not what we measure in practice, right? What we measure is finite charge in a finite volume, and then we measure the size of the finite volume, and then we can make the ratio of the charge within the size of the volume, and then we make these things smaller and smaller and smaller, right? And on the assumption that both quantities are additive, that is, if I take a volume, I divide it into two, right? Then the total charge is the charge of this plus the charge of this, and the total volume is the size of this plus the size of this. If I have that assumption and I make this limit, I can define a charge density, right? But if I can't do that because I can't make this limit, or the additivity does not hold, I'm not going to be able to use this assumption. Therefore, I'm not going to be able to say, oh, yes, there is a charge density. Because you see, the charge density is not the thing that physically exists. The thing that physically exists is the finite charge in finite volume. And this is where we have all the math that we have for physics backwards as what it should be. Because all the math that we do, our point set topology, our differential geometry, all that, you start with points, and then you define infinitesimal things on points, and then you integrate. But that's not what we do in a lab. In lab, we start with a finite thing, and then we say, oh, yeah, I'm going to make these things smaller and smaller, and then that's where you get the points and so on. But the points and all those things exist because you're assuming you can make the limit.
Yes.
So now, if you start with the math and you assume the points, you already assume that you can make the limit. But if you can't make that limit because at some point you get to Planck scale, or because, for example, the mass is not really additive into volume because you have something that goes on the surface between them. So it's not true that the sum, the total of the mass is just the sum of the mass in the volume. Same thing for entropy. Your entropy sums only if you're assuming that things are independent. If they're not independent, that assumption, right? And so this is, again, this is my game. I need to understand what are the things that I'm assuming at the top level such that I can make those limits and I can define the points and the mathematical objects, right? And so what does it mean that a theory is applicable in a specific case? Oh, it's just whether the system that I have in front of me happens to satisfy those assumptions that I'm making. So do I have a classical system in front of me? Well, does it satisfy infinitesimal reducibility, independence, degree of freedom, deterministic reversibility, and kinematic equivalence? Yes, I can model it as a classical system. No, I cannot model it as a classical system. I have to use something else.
So the fact that you can infinitely divide a classical system doesn't imply points still?
In the theory, yes, but it doesn't mean that we have points in the reality.
So this would be a great time to talk about what defines quantum mechanics. So go over the litany of what people usually say separates a quantum system from a classical system, and then show why that is false. You have a set of videos, by the way, which I'll put on screen about this.
I have never seen, and this was my problem. That's why I started all these businesses, that I never found somebody that told me, oh, for this system, you use classical mechanics, and for this system, you use quantum mechanics. I mean, you have examples. Oh, if you have a proton, a double-slit experiment, then you have to use these things. But physics, at the end of the day, if you think about it, it's not like mathematics that you have like one overarching theory and you say, okay, these are things that are valid for everything, right? Set theory and logic, or category theory, if you like category theory, because I don't say that, people from category theory. And then you say, okay, these are the things that we always need to assume, and then you're going to have topological spaces, and then we're going to have groups, and then we have things that are both groups and topological spaces, and we call them topological groups. So you have a whole hierarchy of sort of things that you assume in a sort of well-defined sort of uniform way of looking at things. In physics, you have classical mechanics. And when do you use it? Oh, where I have beads on a wire, where I have planets and stuff like that. And then you have thermodynamics. Oh, I use that, when I have the volumes and the gas and the heat. And then I have relativistic mechanics. Oh, I guess I use that when things are really fast. And then I have gravitation. So it's basically, you learn, when you do a physics degree, you learn a bunch of problems, and you learn to recognize patterns. And then oh, I have a new problem, or this problem is closest to this one, and so I'm going to use those things, right? And this is what I find completely unsatisfying. So when I was a summer student at CERN in 1999, then I was sort of asking myself, that's also where I met my wife there. Well, future wife. It wasn't my wife at the time. But the point was that, okay, I was studying engineering at the time. I wasn't doing physics. And I just, wanted to know, like, what are these things? I wasn't really going to read, to another theory. So I said, okay, I'm in CERN. There's a big library. And what I'm sure that there is going to be a book, a textbook, that in the first chapter is going to tell me, oh, this is what quantum systems are, and this is why you should use this thing. And of course, I went through 20, 30 books, and I found no such.
Why don't you ask someone?
I asked somebody. I got no answers. Yeah.
And you got no answers, or you got unsatisfactory answers?
I got the answers. Well, I don't know. I can tell you. This is beats me.
Okay, well,
above
it obviously wasn't a great enough answer that it stuck with you.
Oh, there was no answer. Like the most professors all the professors that I talked to, they admitted not having an answer, and they just point me to somewhere else. Oh, Bell did some stuff. Go read that. I have no idea. And actually, the turning point for me was when a PhD student at the time told me, look, you're never going to find these answers. The only thing that we have is the math. I can teach you the math. And so he taught me the math. And I learned the math badly, like all physicists. And it then stayed there for me. Okay, why do I have that math? right? And then, okay, let's reverse engineer the math. That's sort of how physical mathematics, how reverse physics started. And then I realized, well, I need to actually understand the math a lot better. And that's why